So Tristan now is going to present the CERN control group cores and tools. So Tristan has been part of CERN control group since 2017. He developed the Cheby tools and maintained hdlmake. He is currently working on the White Rabbit technology. Previously, he was working on embedded systems and on compiler toolchain. And he is also the main developer of hdl, an open source VHDL simulator and synthesizer. Tristan.
Yes. And yes. Okay, so the exercise will be not to read the slide because they have been drawn to be in order to be read outside of this talk. So I'm part of one section of the control group. And my section is named BE-CEM-EDL. We mostly do hardware and low-level software for the control group, or that part of the control group, which is in charge of, let's say, I would say, general synchronization of the accelerators, of the control for the accelerators, and we also do a lot of drivers and general boards for the accelerator domain at CERN. And we are mostly well known for being at the origin of the White Rabbit project, which is a way to synchronize clock over Ethernet. And by synchronization, we mean, let's say, 7 nanosecond synchronization over more than 10 kilometers, which is, roughly speaking, the diameter of the LHC. But it's not our only activity. We are also at the origin of the DIoT, let's say, ecosystem, which is a crate for field buses. We are also at the origin of the ohwr.org project domain website. And we are also at the origin of, let's say, Ravier is also the origin of the OHL license. And in addition to that, we also do a lot of, I would say, not so minor, or maybe even major, but less well-known project like Carrier for PCI, VME, and other standard. So one of the particularities of the White Rabbit project, which I think it has structured the working flow inside our section, yet it's a project we started a long time ago, so we had time to improve our methodology. It's also a multi-target project, so one of the White Rabbit core is supposed to be embeddable into any FPGA, okay, which means, roughly speaking, at least Xilinx Altera. So we cannot do shortcut and blindly follow what vendors are selling as a good way to do a design. White Rabbit also there is a HDL part of it, and there is a software part of it, and they are both equally important. The PTP core so the White Rabbit PTP core is an IP, but we have also a full product, which is a switch. So we have mechanical enclosure, we have PCB design, we have HDL, and we have software running on the switch. You can buy it not from CERN, but you can buy it on HDL. And okay, because White Rabbit is about synchronizing clocks, obviously there are a lot of asynchronisms inside. So I will present what we have developed during these 15 years. And one of the first tools we had, or maybe not the first, but one of the tools we had is named hdlmake, which is how we can build the gateway, or how we can do a simulation using vendor neutral representation of the source. So that's the problem that you should have every day. You have a set of sources, and you want to generate a project for your synthesizers, but you also want to use almost the same source, the same set of sources to do simulation. And if you follow what vendor says, you have to write 2 different projects, so you have to update each project or every project each time you change, you add a new source or you remove a new source. All vendors almost follow, have a TCL interpreter inside their tools, but of course the commands are not the same, so we cannot use, it's not easy to use TCL as a command base. You can suppose that describing the set of source is simple because you are supposed to be at the origin of the source file, but it's not that simple once you have a project that goes bigger and bigger. Because first you want to organize source in different subdirectories, and also because you want to use sources defined in a different project or sub-project or core that you have developed and you plan to reuse. And at some point you have to gather all the sources, which is not something that easy anymore. So what we do, what does hdlmake do, use is that it uses a declarative Python file named manifest.py. So you list the file contained in a directory. And at some point, hdlmake will read all these manifest.py files and gather all the sources in order to create your project. Aha. Yes. Ideally, you should use declarative way of Python, so you just have to declare variables, and then hdlmake will use these variables to create the project. But because it's Python, you can use the full power of Python and do some construct in order to, for example, select which source you want according to your target or according to your synthesizer. So for example, in Whiterabbit, according to the target, we use a different file interface. In addition to adding file or listing file in manifest.py, you can also indicate other directories using this module declaration, and then hdlmake will try to read, well, will read the manifest.py contained in these directories. And finally, at the top of your project, you have to describe what you want to generate. So in general, or what we do a lot, is to generate a particular project for a particular synthesizer. And then we have to, so you have to declare exactly which FPGA you want to target using which tool, and probably also adding a constraint file because it's very particular to vendor. So when you have this kind of file, you can just run hdlmake. It will generate a make file, and then run make, and if everything goes well, at the end you have your bitstream. So you can almost use hdlmake without using Vivado or ISE or Quartus. It could generate your project, which is nice also for CI/CD. And this works so on Linux, of course, but also on Windows, which is not always as easy it could be on Linux, because you have at least make and Python, which can be either Cygwin or not Cygwin. All combinations should be possible. It's a little bit tricky. In addition to, so until now I presented how to structure your project with subdirectories. You can also, using in the module variable, declare cores which are outside and just refer by their URL. And the facility hdlmake provides is to automatically clone the repository, the outside repository, or update it. And using that, same, you can do hdlmake fetch and hdlmake make, and it will create your full, it will generate your bitstream at the end. What we do, we don't use hdlmake fetch a lot, we usually use a submodule within Git, and we manually update the submodule using Git submodule update. And okay, that's something could be discussed. Maybe it's very technical and could be discussed outside, but this is our current way of structuring the project. There are pros and cons we can discuss. And if you want to share cores using multiple projects, so instead of checkouting and cloning cores in every project, you can try to share it by overriding the fetch to variable. Again, it's a little bit a trick on the outside. So this is not a very revolutionary idea. There are similar tools like this, like FuzzSock and Hog. I think there are people from, at least from Hog here. One of the interesting points of hdlmake is that it doesn't enforce any particular methodology. You can use it partially, for example, just to gather the sources. It will create a tickle script for your application, and then you can use a completely different set of scripts in order to add some constraint or whatever you want. You don't need to use hdlmake from start to end. You can use only to get the sources, which is already quite nice. So that's how we build project. Now going a little bit backward or inside, how we generate sometimes a part of the project automatically. So again, this is not a new idea. Many cores have use a CPU or it's almost related to CPU, and they have a memory map in order to connect software and hardware. Writing this register inside the memory map it's already a little bit tedious because you have to, it's always the same code almost. And you want to have the hardware view, so the HDL file, and the software view, which is either the address of each register or a struct in C, which represents the whole memory map. And of course, they both must be in sync, otherwise problems will arrive. So this is not a new idea, and there was at least two tools written by different teams at CERN, named Cheby and BE-CEM. And so when you have two competing tools, the best idea to merge them is to create a new tool, hopefully replacing the existing one. So what can you do with Cheby? So first, the input file is a YAML file, and you just have to, you create a header describing what is your memory map and what is the bus of the memory map. So in Cheby, there is, we support Wishbone, Axie4Light, Avalon, and a few others, which cover already a lot of standards. And you can also choose your InDNS if necessary. And then when you have your header, you can list all the registers, and mainly you need to indicate names and the access mode of a register. Usually you want to go a little bit to have a finer granularity, and you want also to describe fields within a register, so you can do that in Cheby. You just have to describe, to give a name for each field, and also to give which size is each field. So this is what you use for a 1-bit field, and this is what you use for a field which requires several bits. In addition to that, in addition to register, you can a little bit tailor what you want to generate, and there is a concept of extension in this YAML file, which always starts with X. And you can, for example, specify that for the HDL part, it will be in fact a constant, so there will be no input port of the HDL side. You can only, there will be a constant inside, and you cannot modify it. The idea with this extension is that you can generate multiple format, or you can use the same file for multiple use. So we generate HDL, we generate header file for C, we generate documentation, but you can also generate a different format for other tools, and you can still use the same tools, same file format, and if you need to add some description, you can use this extension in order to specify the behavior for certain generation, which makes the tool rather flexible and extensible. Okay, a little bit other example. You can generate in the HDL, you can specify that a bit will be automatically cleared. So for example, it will be only a pulse. So when you write, the bit will be cleared at the next cycle. Or you can collect input, or let's say ones, with or clear name. So each time there is if there is a 1 on the input, it will stay in the register until you clear it. There is also flexibility in how we generate register. So basically, we just have a register and you have the output. If it's an input, you read, there is a port which is read. But if you want to do some fancy behavior, for example, if you want to connect a FIFO, you need to know when the user read from the port or when the user write. And there is extension in order to have additional signal in order to do whatever you want. So this is what I already said. So we generate many things from this YAML file. And in addition to the register, you can also describe memories. We can repeat multiple times one structure. So for example, we can repeat a single register, or we can repeat a memory. We can add some map, which is quite powerful. So you can, let's say, include or refer to another file in a file. So you can, let's say, gather many IP into one file, or you can just group elements. So this is, for example, how we generate, how we use some map. So here, this file will say that at address 0, there will be what is described in this file, which that's how we create IP composed of multiple IPs. So this was a very quick introduction to Cheby. General cores. So you had two presentations about cores, and this is a third one. I think this is a little bit a problem, at least at CERN, because there's accelerator community and experiment community, and they don't speak a lot together. Well, it's almost a different world. And even within, okay, so I'm part of the accelerator community. Even within the accelerator community, we have different departments and different groups, and they speak together. Maybe not every day, but they speak together. But they don't always share code together. So it's a bit out of islands. So I don't want to make advertisement for our library. I just want to, I'd like to have, okay, ideally we should have at least in the accelerator sector, we should have only one library. I'm not sure it will happen, but let's try to contribute. Okay, maybe one of the specificities of our library that we are using the wishbone bus extensively. So there are a lot of cores related to wishbone. And then we have cores that you can find everywhere, like memories, FIFO, we have synchronizer. Okay, there are good reasons to have one repository with many cores. At some point, people wanted to have, many to split the core, but I think it's not an idea because it's not that easy to add a new core. So we try to promote adding new cores. Another difference between maybe other libraries that it's supported by hdlmake, so there is it will automatically interface easily with hdlmake. And obviously we have a style which is not fully unfold, but we have it. We have RAM and FIFOs, synchronous, asynchronous, initialized, not initialized. Yeah, at the end, it's what we have used, and we have accumulated all the basic blocks into this library. And because it's used by Waterabit, it works at least with Xilinx ISE, Xilinx Vivado, and Altera. We have synchronizer, at least basic one. So there are attributes in order to constrain, and there are also script to generate additional constraint, at least for Vivado, in order to be correct, I would say. In addition, we have also a reset generation for multiple clocks, so the shortened reset is generated for all the domains. So we mainly use Wishbone as our SOC bus. So we have an infrastructure for Wishbone, crossbar, adapters, and pipelining. In addition, we use, this is the traditional techniques in VHDL. We use records to describe, to group the input and the output of a Wishbone port. We cannot use system Verilog interfaces because I think it's not very, first it's mostly VHDL, and second, I think it's not completely well supported with ISE. We have SPI, S2C. They come from OpenCore. We added some wrapper in order to make it easy to interface with our Wishbone interface. And we have drivers for Linux driver for at least some of this core because we use it on Linux and test benches. And that's all for this talk. Thank you.
Thank you, Tristan. Any question for Tristan?
Hi, thank you for the great slide. Can you go to the previous slide? I think.
Just the previous one?
Yeah, I think my question. So any possibility to add more drivers here, or is there a need at CERN or to add more peripherals here, and they're supporting driver and then community to access it?
I would say just create a merge request. For the cores are available on GitLab CERN. I don't think it's. I think it's open it's visible by anyone. The only problem is you cannot do a merge request if you are outside CERN. But yes, you're welcome.
Okay, yeah, but my question was that SPI, I2C are, let's say, quite old. They are faster buses that are coming up, right? So maybe CAN is faster than SPI and I2C for communication between devices. It's more robust. Or there are a lot of new Ethernet standards that are coming. So at CERN, do you need to use these kinds of things, or any plans to use the new peripherals apart from these traditional ones?
Okay, Okay, it's a multiple answer. First, in general cores, we only want to use cores which are quite small. If you have something which is much bigger, I think it deserves its own repository because it's a different way to maintain it. Okay, I2C and SPI, okay, they are everywhere, and I suppose almost any design use one of them because it's everywhere. Now, if you need more performance in communicating between chips, we don't have any specific cores for that.
Okay, so you use the proprietary one from the vendors.
No, but we don't. Okay, we don't have this. I don't think we don't have this kind of. I don't think we have this kind of issue in our design. Okay. Most of our designs it's only one FPGA, so there is no need to communicate over FPGA. Or when we need, okay, few design we need, and we add just a custom link.
Okay, thank you.
There is one in the front.
Thank you very much for your talk. Actually, I've seen that the tools you presented, hdlmake and Cheby, they are super flexible. And I was wondering, in your opinion, if we have a project with many configuration of the IP cores, and what do you think that it's the philosophy to regenerate the project which is more aligned with these tools? For example, would be to keep these YAML files that you described that has all the configuration, no, of the IP cores, and to regenerate these VHD files, or maybe it would be more like releasing when you commit the configuration to release that IP core with a specific configuration. I mean, when you develop this tool, do you have like a philosophy in mind, like, or it's just you have the tool and you can use it as you wish? Or no?
Okay, I'm not sure to have a particular philosophy.
Thank you.
Okay, to comment a little bit. First, with at least with Cheby, there is no real possibility of parameterizing the register map. It's something I think we don't have the need of that, or not enough in order to do something spectacular. How we use it? Concretely, we had, in our design, we had a script in order to call Cheby, and we call it manually, and we commit the result of this, what is generated by Cheby, so that users don't need to run Cheby or by themselves. It's just one way to generate sources, and we provide the sources in the repository. I don't know if I answered your question or not. Okay, we don't want to add dependency for the user, because they say, I need hdlmake. Oops. No, I need Cheby. Oops. Let's try to limit it a bit when possible.
Thank you.
I have a question. On Cheby, you showed the description of the buses side as the example. But what happens? Maybe I missed it. What does it look like from the HDL side? What's created on that side?
Okay, that's something I didn't speak about. So from this example, we generate one. It could be VHDL file or Verilog file or system Verilog file, and at the top you have clock reset, and you have your main bus, so wishbone, axi4, and then you have input or outputs or bus for every register. And if you describe it, if you add also a sum map, you can also it can also create a bus to connect to another core. And the interesting feature that it is able to, the tool is able to convert from, for example, wishbone to Axie4. There is no problem with that.
So the memory, is it created by Cheby, or this is a thing that then connects to the memory?
Okay, for memory, you can do both.
Ah, okay.
Okay, it's a little bit particular.
One last question.
Thanks. Yeah, just on this slide, actually, you list a couple of slave buses there. Is there any support for IP bus, for instance, which is pretty well used?
If I'm not wrong, IP bus is something you send over Ethernet.
No, it can run over PCIe and many other interfaces.
Oh, this is not the same IP bus that I know.
With IP bus, you will have also the thing to generate that. So let's say that IP bus is a competitor to this, because you will have different address maps that are XMLs, and you will have to use those. It doesn't really make sense to use IP bus if you want to use Cheby. I'm not an IP bus developer. I'm just a very keen user. But I think we have IP bus developers in the room. No? They left.
No more questions? Comments? In the back again, sorry.
That's fine.
That's good for my belly. Sorry.
No, I just have a question regarding the White Rabbit project. Because, okay, you have shown, probably this has no direct relationship, but because you have shown a lot of cores, a lot of building blocks. However, with White Rabbit, okay, part of the synchronization can be done. I know that there are some specifics of hardware that you have to do also on board. However, I know that you can use gigabit transceivers to do that. How do you handle, for example, because between Series 7 and Ultra Scale, there's a big jump on the gigabit transceivers that are specific from the vendor. How do you handle this type of challenges?
Okay, so we use a transceiver from the vendor, and then we have, I would say, a little bit of adaptation layer. And then we have a common interface inside White Rabbit. Okay, in particular, to talk it a bit more. For example, most of the Xilinx transceivers, they don't provide any indication of how they slide bit into words. So you don't know what is the delay added by the transceiver. So we had to disable this feature inside the transceiver. So we don't enable bit sliding, and then we do it manually, where we know exactly how many cycles we spent into gathering bits.
Okay, but it's a
different
like layer. Yeah.
So there is a big part. Okay, no, not a big part. It's there is a part which is completely which depends on the transceiver we are using.
Okay, thank you.
Thank you. So we can thank Tristan again. We have to move on.